Okay, so here we go. We are just going to compute directional derivatives directly from the definition and see how this works out. Okay, so we have dfa is d by dt, t equals 0, f of a plus tv. There's just a definition of directional derivative, right? Okay, now we're given a couple of things. It looks like we are given that a is x naught, y naught. And we are given that the vector v has coordinates v1 and v2. And so with that, I can rewrite as f of x naught plus tv1 and y naught plus tv2. Is that cool? Yeah. Okay, now see, what is our function f? Our function f is, oops, e to the x minus y. So that's what we're going to be plugging this x and y into. E to the x minus y. Okay, all right, I can remember that. All right, so e to the x minus y good? Okay. Now, just as a convenience, let me rewrite this a little bit. There is, you'll notice, I mean, x naught is like x naught, v1, y naught, and v2 are all constants, right? T is the only variable here. So e to the x naught and e to the minus y naught, those are just constants. So I'm going to pull those out. In fact, they can even come all the way outside the derivative. And so let me just rewrite those as, whoops, e to the x naught minus y naught, and then I have d by dt. Let's see what's left over. Well, there's tv1 and then minus tv2, so let me rewrite that as e to the tv1 minus v2. So a little bit of algebra there, but is that algebra all okay for everybody? Okay. All right, well, now the derivative. Well, the derivative is no big deal. That's just single variable. Single variable calculus here. And so I have e to the power of t times a constant. So when you take the derivative, that constant comes out, and I get v1 minus v2. And then e to the t v1 minus v2. And this all evaluated when t equals 0. Cool? Okay. So now we plug in t equals 0. That's fantastic, because that means I have e to the 0, which is 1. And so altogether, I have e to the x naught minus y naught, and then times v1 minus v2. Now, that's kind of the answer, but the question asks something a little bit more specific, to write your answer as a matrix vector product. So in particular, I want to view this as being some matrix times v1, v2. Right? And you can just kind of strategize and think, all right, well, what in some sense has to be in each of these places? And so it's e to the x naught minus y naught, and then minus e to the x naught minus y naught has to go there. So this then is the matrix. Just to emphasize, it has these two entries, so it's a single row matrix. That's the derivative matrix for this linear transformation. Yeah. Well, now, of course, when this question came up, we hadn't used the term derivative matrix, and we certainly hadn't said Jacobian matrix yet, right? Mm-hmm. But we had said linear transformation, and the way we recognize that this is a linear transformation on V is by recognizing that it can be represented by a matrix. So, yeah. Everybody happy?
Mm-hmm.